So a new way to talk about an old idea, and not old like it's, getting gray and old and it's time to move on, but actually a pretty major idea in calculus, the equation of a tangent line. Actually, I always like that this lesson typically ends up right close to the midterm because, well, you're going to be tested on this on the midterm. And so now is a great time to sort of ask the question, do you remember? Well, do you? Do you remember how to find the equation of a tangent? Okay. You're here. You're thinking, I hope. Why don't you think about this one? What if you were taking the midterm right now and you had to answer this question? What would you start doing? It doesn't really have a little rhyme to it, but when in doubt, derive. In baseball, when in doubt, call him out is the little, you're out. When in doubt, call him out. But in calculus, when in doubt, derive. Again, it doesn't quite rhyme as much, but are you doing the derivative? Are you doing the derivative? Remember, when you do the derivative, that gives you a slope formula. Of course, I even, with a little mean to you here, how do you do the derivative of a square root? If that's causing you to not get going here, you have to think of it as an exponent of 1/2. And of course, you bring down that exponent and then you subtract from it. Don't forget to do the chain rule, but it doesn't actually matter because it's only going to multiply by 1. But don't forget. Are you really working through the whole problem? Are you trying to find an equation of a tangent? And if you think you have all that, maybe you graph it. And, well, what are you looking for when you graph it? All right, I like that you guys are trying, and we have a lot of things that are right, which is good news. Again, you'll definitely see this on the midterm. If maybe you need a little help with it, you can still keep learning and keep getting some help. I'm just going to simplify this. Not really much happens except that I kind of get rid of the negative exponent. I just don't like negative exponents. I actually changed it back to a square root in the denominator, which, we kind of look the other way because really it's not that big of a deal if that square root's down there if you're just going to continue plugging in. And that is a key step. Make sure you plug in the number 3. But of course, you plug it into the derivative. Okay, so when you plug in 3 to the derivative, you actually are getting the slope of the tangent. Looks like it comes out to be a 4th. It's a pretty popular idea, the slope of the tangent. Can you turn it into an equation of a tangent? Okay, so what else is needed here? You want to be thinking y equals mx plus b. Y equals mx plus b. Okay, it is a little bit more algebra at this point, but you actually have to, one more time, mess around with plugging in 3. Remember, you're plugging in 3 because you want to get the y value that goes with it. It's a good chance you're going to need x and y. So now that we know that 3 comma 2 is really the point of interest, now we can get about the business of y equals mx plus b. So why are we talking about this again? Why? Good. That's a good question. I like when that's brought up. Let me try to give you a good answer for that. To answer that, let me show you when it is plus or minus. It's plus or minus when it's a solution to an equation. It's plus or minus when you put the square root into the problem. It's plus or minus because we all know that positive and negative 3 can square to be 9. So how's that different than this problem? Well, you see, this problem, it was given to you, first off, it was given to you as a square root. It wasn't that you put the square root there. But because it was given to you, and here's really the answer to your question, it was only given to you as a positive because, well, it wasn't given as a negative. If I wanted it to be a negative, honestly, from the get-go, it would have been given to you as a negative. So I guess what we're saying is I gave you, just like in any problem, a certain sign. That certain sign just defaults to positive. What do you think? It would almost be the same thing as me just saying, here, Delaney, here's 10. And that's very different than me saying, here, Delaney, here's negative 10. So here I just gave you a positive. But that's a good question. I'm glad you're thinking about that. That means that we only have one y value and, of course, one equation. Okay, so that equation, I see a lot of you have it correct, but that equation can be found by plugging in for y, for m, and for x. Do a little bit of math, and you end up with 5/4. Yeah, you end up with 5/4 or a decimal. Yeah, okay, so then we have y equals 1/4 x plus 5/4. Now you're probably hoping, I would assume, that we're going to do something new with this, and that we are. But the truth is, to be able to find that equation doesn't change. It's always going to be the same technique. So consider with me maybe a familiar looking graph, or maybe not. What do we have here? We have the square root of 1 plus x, and we have our tangent equation. I actually don't have to put parentheses around these fractions just because they're simple and have one term. I want to make the tangent line bold just so it looks different. And I'm going to change the window a little bit. Don't worry, it's not like I expected you to know this, but it just kind of lets me zoom in on the action a little bit. All right, so here comes the curvy line. It's like a square root line. And there's the tangent line. Now it's doing what we would expect it to do. It's just kind of touching, we call it being tangent, at x equals 3. Okay, so this is good. We know that we're right. Now consider with me what would happen if we actually zoomed in around x equals 3. Now if I zoom in around x equals 3, I'm going to make my x values only go from 2.5 to 3.5. And I also know that my y values, it would be helpful if I kind of close in on those. Okay, again, just watch. You don't need to do this on your calculator necessarily. But I do want you to, well, hopefully observe something. Now here comes the square root graph, zoomed in at x equals 3. And then quickly you'll get the tangent graph. Square root graph, tangent graph. Just show it to you one more time. To do that, I have to pretend that I changed something. Square root graph, tangent graph. Now, I'm not trying to pull a fast one on you. Everyone here is smart enough to realize that they're two different equations. In fact, one of them is definitely nonlinear. It's a curve. One of them's linear. It's straight. But what I am trying to help you see is if you zoom in on the point of tangency, x equals 3, that it can appear that they're the same. I want you to say that it appears that they're the same. In fact, they're so much the same that we're able to make a statement about this tangent line. And that statement is that it approximates our linear line. We call it a linear approximation. Now just think about what's happening here. It's not really that earth-shattering. We're just saying that a straight line almost looks the same as the curved line. And because it almost looks the same, we can say that it can approximate it. And what we call a linear approximation, we call that a linearization. It's a linearization. It's kind of like we linearized, I'm not going to write that word, the curved line. Now, to kind of, put the definition down, the sort of the textbook answer, but it's still important. A linearization is a tangent line. In fact, actually forgot, but it's easy to fix. We give it a new name. We call it L of x. I should have did that up here. We give it a new name. We call it L of x. So L of x is this tangent line. It's the equation of the tangent line, actually. And again, it approximates the original function. It approximates f of x. Now, it should occur at some point. Maybe it already has, maybe it will soon, but that you'll say, well, why would I want to approximate numbers? Really, why would I want to approximate things if I can just get the actual answer? And the answer to some of that is that this goes back to the theories and the discoveries and the beginnings of calculus. You guys will actually watch a little movie, a little video about Newton and Leibniz, both what are called the fathers or the founding fathers of calculus. And what I'm getting at is that back in those days, before there was calculators and ways to actually compute numbers, it actually was very helpful to be able to approximate things using linear calculations, because things that are linear are arguably simpler than things that are nonlinear. So I'm just being honest with you. Some of this lesson is a little bit of kind of the history of calculus and just that you go through that theory. Okay, and we're going to do the theory. But the truth is, we're actually going to be doing some approximating. And sometimes kids like, why would I want to approximate? Okay, and again, it's a little bit before we had some of the modern tools that we have. Okay, and it's also going to show you some connections. We're all about connections, so that's important too. So let's find the linearization. It's easy because it's the same thing that we studied is the idea of a tangent line. But then we'll do some comparing, and that's kind of the new idea. So let's try it. Find the linearization. I just kind of want you to see those directions. When you see this language, when you see the language, find the linearization that you say, okay, I'm finding that tangent line. And I would have to give you a function. So a lot of times we'll do a function that is not linear. I mean, that would make sense. We're going to do a function that's kind of fancy. So the ln of x squared plus 1. Honestly, the other reason I'm doing this function is because, well, again, that midterm's a week away. And do you remember how to do the derivative of ln? Okay, it might be something that you study, or maybe right now when we talk about it, it sort of comes back to you. But you definitely have to do the derivative because we need the slope and all that good stuff. Derivative of ln. Are you digging back a little bit into the recesses of the old brain there? It's a rule. It's 1 over. Is that what you were thinking? It's 1 over. It's actually 1 over u. U, though, is the inside. It's x squared plus 1. Careful. True or false? False. Because you have to do the chain rule. Okay, so always do the chain rule, and we end up with 2x. So 2x over x squared plus 1. Okay, of course, that's the derivative, so we can find the slope. And we'll do this together, but I don't think that this is going to blow you away too much. Oh, I forgot the place. That's important. That's kind of my bad. I forgot to put the place. Bless you. We like to use the letter A. Okay, we like to use the letter A. Just so you understand, it would be the same as the letter X. But sometimes A is used to describe, again, a place or a point. So at A equals 2, and of course, that'll be our X value that we can plug in. All right, make sure you're plugging it into the derivative versus plugging it in maybe to the original equation. Of course, not yet. We want to plug into the derivative. Okay, get a little 4 over 5. All right, now, even though we've done it before, I don't want to spin this like, just kind of whatever. Let's make sure that we're doing the equation correctly. When you do the equation, you always need the y value that goes with 2. Well, we got to find it. And it's okay to think of this value as a function of a log. In other words, it's okay to say the log of 5. It's also okay to get the decimal, but kind of want to throw this at you here because it is the way that's a little more formal, and you'll see it in the solution manual, so it's definitely acceptable. So there's your y value, and you're going to plug ln of 5. You're going to plug that in for y. Of course, we've got our slope of 4/5. We've got our x value, or the a value of 2, and then we end up with solving for b. So again, what I'm actually showing here is that it's okay to write your answer in terms of a function. The ln of 5 minus 8/5 is your b value. And I'm not going to turn that into a decimal, just for something a little different. But you do want to write the linearization and take a look, since it's kind of the new way to do it. We're going to write it as the ln of x. Yeah, I want you to write as the ln of x, not necessarily y equals. And you've got your slope times x plus this kind of goofy y-intercept, ln of 5 minus 8/5. Now, as I already said, you could turn it into a decimal, but I'm presenting it because you can also leave it this way. Now, a lot of times what we do with the linearization problem is we will compare it. Like, we'll find it, okay, but we're going to compare it. And what we're going to compare is basically two y values. We're going to compare a y value that is on the linearization to a y value that's on the actual function. I don't know if I want to break this up over lunch, but let me show this to you. And we're going to have to continue then. Okay. Again, this can get a little bit more hairy, but this is just a y value that's really close to the original y value. And this is also going to be a y value that's really close. And I'll explain a little bit more about what this a plus 0.1 represents. All right, let me show you what this whole a plus 0.1 thing is. It appears kind of random, but it actually, I hope you say, okay, I got that. Remember, you've got the curve, you've got the function. It's probably nonlinear. And then you have this tangent line. And of course, the tangent line is always linear. So what we like to do is we like to compare. Now, if we're going to compare, we need to compare a new x value. So here's kind of the part where people are like, well, why is it 0.1? Well, it's not like it's just 0.1, but it's my new x, it's my x value plus 0.1. It's like a new place. So it would be maybe like right here. It would be at a equals 2.1. Now, at this new place, I guess shouldn't call it a. I guess we'll just call it x. But at this new place, at this 2.1, I'm going to end up with two different y values. I'm going to end up with what we would call the actual y value. That would be f of 2.1. And then I'm going to get what we would call the estimated y value. And that would be L of 2.1. And look, they're similar. Okay. In fact, if you remember the one I showed you on the screen, they're probably going to be like almost the same. That's kind of the idea. We're supposed to notice that, oh, okay, they're like almost the same. So let's notice. We're going to do L of 2.1. Make sure you're not getting too bogged down with the notation. The notation just means plug in 2.1. Now, you're going to plug in 2.1 to the L equation, that 4/5 x thing that we got. And we also have all that ln of 5 minus 8/5. When you plug in 2.1, you get a y value. Again, kind of basic math, but you get a y value. Now, I haven't really used the calculator yet because I'm always trying to help you guys to think no calculator, but you'd have to use a calculator to compute that. It's going to be a decimal. We need to see that. And we usually say, let's get a couple more decimals than normal, maybe out to 3 decimals, because again, it's going to be something pretty precise. And then we want to find f of 2.1. Again, why is it 0.1? Just because 0.1 is really close, it's going to make sure I'm really close to where I started. Okay, now when I do f of 2.1, I'm back to the original equation. ln of x squared, 2.1 squared plus 1. Now, when the fathers of calculus, like Newton and Leibniz, and you'll learn about them a little bit, when they would have had to compute this, they didn't have a calculator. And I'm not even really sure how they did it. They probably had charts and tables. But the point is that this is a lot harder to calculate than what we did up here, even though I realized that also had a log in it. But that's kind of the theory anyway. But we have a calculator, and you would punch it in. I'll tell you the number. And the whole idea is that they are similar. They are similar. In fact, what we usually will do, I think the book will ask you to do it, is to find the difference. Sometimes they call it the error. I actually kind of forget what language they use all the time, but whether they say the difference or the error, or if they just say to compare them, that implies that we want to, in fact, let me just use the word compare. That probably makes more sense, but we're just going to subtract the numbers. Okay, we're going to subtract the numbers. And we find out that they are only differing by not a tenth, not a hundredth, but a thousandth. Okay, and that's, I don't want to say it's always going to be that number, but it's always going to be something small, relatively speaking. By the way, the reason we don't just stick with the original x value, this is worth noting. The reason I don't actually just plug in 2 is because it's going to be the same. If I just plug in 2, it's going to be the same value for both of them. Okay, because that's the place that they both share. But if I plug in something close, then I can compare. All right, try one. And when I say try one, it's kind of like this whole thing. You're going to find the linearization, and then you're going to do a little comparing and find out if you feel good about it. Plus, let me mix things up with a trig function. So we're going to do the sine of x at a equals pi. The sine of x at a equals pi. And of course, this time you do the calculations. You actually use your calculator and see what happens with your numbers. Remember, if you're having a little trouble kind of remembering, it's been since lunch, you got to do the derivative. You got to find the good old equation. You got to find the good old equation, but we call it L of x. Okay, but the good news is that's what we've been doing and have done for quite a while. Depending on how much you love trigonometry, there is actually some nice unit circle stuff in here. You get numbers like -1, you get numbers like 0. But again, you can use your calculator, especially when it comes to the comparing. Just double check. I want you to get the correct linearization. The y-intercept is pi. The y-intercept is pi, so your linearization is actually a little L of x equals -x plus pi. L of x equals -x plus pi. Is there anything that happened here? Is there anything with getting the y-intercept? I kind of just slid this 0 in right here. That 0 came from plugging in pi right up here in the good old sine equation. So how'd you do? Did you realize that it's not 2.1? Okay, sometimes I see 2.1. It's not 2.1. It's pi plus 0.1. Pi plus 0.1. You know, you can use the pi symbol, but really you're plugging in now not 3.14, but 3.24. Okay, you're plugging that into the little L of x equation. You will have a calculator, but as I've said, sometimes some of you might end up in a college course, some of you might, where the problems are designed that you don't need a calculator. I mean, it just so happens that the pi's cancel out. If you do a little bit of that math, it might be easier than using a calculator. So you end up with -0.1. Now, remember, -0.1, that's not just like a random number. That's the approximated y value. That's the approximated y value. Tomorrow, even though I'll be absent, the video that you'll watch, you'll be discovering another approximation. So there's a reason I'm kind of mentioning right now that that's an approximated y value. You might just want to highlight that, so tomorrow you don't confuse it. And then you do f of pi plus 0.1. F of pi plus 0.1 is like doing the sine. Now, again, kind of, I guess if you can make an argument for why are we doing this, now you need a calculator. Okay, now you need to use a calculator to compute the actual value. Sine of pi plus 0.1. Well, I think if you look at the decimal places, you could make an argument for 0.99. Sometimes kids will say, but that's almost like the same. I mean, if depending on how you round it, it actually comes out the same. It's not technically the same. I'm going to leave it as something different. But if I compare them, now when you compare numbers, you subtract them. I think the book used some language that says that it can just be like an absolute comparison. An absolute comparison would mean it doesn't matter if it's positive or negative. We're just really trying to find the difference between these numbers. So, you know, you actually could subtract them without the negatives. You could subtract them without the negatives. But we end up with I'm having trouble thinking about that subtraction. 0.1. Having a little freeze point here. 0.1 minus 0.99. Oh, 0.001. 0.001. Again, you may compare them without the negatives. Is fine. Okay, they're almost exactly the same. And that's kind of the way it's supposed to be. They only differ by a small value. Approximating y values. Approximating y values. Tomorrow, you're going to approximate the change in a y value. You don't need to write that down. It'll actually be the first thing you'll see tomorrow. But today we approximated just a value. It's called a linearization. Tomorrow we'll approximate the change in a y value. It's called a differential.